Hello there and welcome. This video is on section 5.5, using the method of integration by substitution to find integrals. So let me first start off by trying to dispel sort of an incorrect name here. This is not really integration by substitution, even though that's the normal vocabulary that's used by mathematicians. We're not really doing any integration by substitution. What you're doing is you're simplifying or simplification by substitution. This is really an appropriate word for this or name for this. Substitution, if I spell that correct. So we're going to be using an algebraic simplification technique called substitution. And you may have seen this before, perhaps in a pre-calculus class when you were trying to factor complicated things. You first started factoring not so complicated things, maybe x squared plus 3x plus 2, and that works out to be x plus 2, x plus 1, no problem. But then you ended up with like some trig functions, and you had perhaps sine of theta squared plus 3 sine of theta plus 2. And we're asked to factor that thing. And although there aren't really special factoring rules for sines or other kinds of things, what you were exposed to, hopefully, in a pre-calculus was this thing can be thought of as x. So we have an x being squared, and this thing right here would be 3 times x. And this trig version is really the same as this algebraic version, just that we're using sine theta in place of x. In other words, we've done the substitution that sine theta is going to be written instead by the letter x. So this is what a substitution is. We're creating a new sort of variable or whatever name for something and substituting that. And that's really what we're doing here in calculus. It's a little bit more complicated because we have more complicated problems, but in essence, that's all we're doing. We're just substituting a new variable in for something that's complicated. My example is we substitute the variable x in for the complicated sine theta. So we're going to be doing that thing as well. Typically, the letter that mathematicians use for their substitution is not x. They use the letter u. So a lot of people will call this u substitution or u sub, because traditionally they use the letter u as the new variable. You can use whatever letter you like. You do not need to use the letter u. I'm going to use it because that's the traditional one that you will see in the textbook and in other sources. All right, so let's see some examples after that preamble, after that disclaimer there. So in example A here, we have an integral. And this is not a known integral. There's no formula for a parentheses of stuff raised to the 99. If I look on the formula sheet that I have available on Canvas, you have x to the number, like x to the 99. We know the antiderivative of x to the 99, but this is not the same as x. It's a parentheses. It's kind of like a chain rule thing in some sense. It's an inside function raised to the 99. So the formula isn't precise. It doesn't match. I mean, the formula here doesn't match our problem. And so the idea, and there's no chain rule for antidifferentiation, unfortunately. What we need to do is simplify this so it looks like x to the 99, or at least some x to a number, right? It needs to look like that. And what we're going to be doing is this u substitution thing. So this first example is a pretty straightforward one, and all future examples will just be versions of this, just with a little more complicated types of substitutions and a little more complicated algebra, but they all follow the same sort of pattern or same strategy. So the first thing is I'm going to identify something that's complicated that I would like to get rid of. So in this particular case, the thing inside the parentheses, the 2x minus 5, is the complicated part. If I could just imagine that was just x, and I had x to the 99 instead of 2x minus 5 to the 99, the problem would solve itself because I have the formula for x to the 99. So identify some portion that you would like to get rid of, and we're going to make that be our new variable u. So we're going to say u is equal to 2x minus 5. All right, so that's the portion. Now, you can try to let u equal 2x minus 5 to the 99, but as we'll see later, that ends up being a little bit too much to write as a single variable, and the math just kind of doesn't follow itself out. I'll show you examples of how incorrect choices for u will work themselves out, but I want to be just more straightforward in the beginning and just show you how it works. So we're choosing u to be this inside function, this 2x minus 5, this complicated part we want to get rid of. And so instead of 2x minus 5, we're going to have u to the 99. Now notice we have a dx. And if you've been forgetting to write the dx, well, first, shame on you. And second, this is where it's going to really come back to really matter, right? So we have a dx here. Now, the formula we have that we can use is x to the n dx. This x and this x, this variable and this variable have to match. It cannot be x to the n dt. It can't be u to the n dx. The variables have to match. And they do not match in our case. We have u to the 99 and we have a dx. So we cannot use that formula because the variables don't match. However, there's a very easy way of getting rid of the dx and writing it in terms of u. Dx is a differential. It's like the dy dx kind of thing. This is our formula. So I'm just going to differentiate this formula. I'm going to differentiate both sides with respect to x because I want a dx kind of thing. So you may remember this kind of chain rule, implicit differentiation kind of thing. The derivative of u, let me put a little bar here. The derivative of u is called du dx. The derivative of 2x is 2 times dx dx because the variable matches the independent variable. I'm not going to write dx dx anymore. I did that a whole bunch in the previous chapter. It's just going to be 2. The derivative of minus 5 is 0. So du dx is just equal to 2. And I can use my algebra now to solve this for dx. I can certainly write this as du is equal to 2 dx by multiplying both sides by dx. And then I can divide by 2 on both sides. And I have my formula for dx. dx is du divided by 2. So now I know how to get rid of this dx. This dx is precisely du divided by 2. Okay, so now I can complete the substitution. I substituted for this 2x minus 5 part and got u. And now I'm going to substitute for the dx part, and I get du over 2. Divided by 2 is a multiplication or division by a constant, and they do not affect derivatives or antiderivatives. In fact, most times when we do antiderivatives, any constant multiple, we're just going to bring on the outside. It's actually divided by, so I have to write this as 1/2 integral of u to the 99 du. So just to recap what we did here is we started with this problem, this question, which was find the antiderivative of this function. And we used algebra to change this into this function right here. So there were no calculus things that were going on. I mean, I guess we did a derivative so that we could find what dx was equal to. So beyond that, there's no integration, there's no integrals going on. We're just algebraically simplifying this into 1/2 integral of u to the 99 du. But u to the 99 du, the variables match. It's like x to the 99 dx or t to the 99 dt or u to the 99 du. We know the antiderivative of that because that's just the power rule. I ran out of space, apologize, so I'll have to go over here. This is equal to 1/2 times The antiderivative of u to the 99 du is u to the 100 over 100 plus c. And that's the same rule as the antiderivative of x to the 99 dx, just different letter that we chose for u. I can rewrite this as u to the 100 over 200 plus c by simplifying the two numbers. And please note that u was our variable. U was not part of the problem. If you look at the problem, there's no u's in this problem. There are just x's. So you cannot leave your problem with some made up variable in here. You can't just make up a variable and say, well, that's my answer. It's going to be this u thing. You have to put it back in terms of the original variable, the original information in the problem. So how do we do that? Well, the way we do that is go back to the original substitution. If I go back to this original substitution, it's right here. Box it right here. U was equal to 2x minus 5. That was our original u substitution. And so we know what u is. We know that u was our choice, and we made it equal to that inside function, that 2x minus 5. And so we can finally write our answer. Instead of u to the 100, we write 2x minus 5 to the 100, because that's what u stands for, divided by 200 plus c, of course. And that, my friends, is the answer to this problem, using substitution to first simplify the integral and then integrate it using our formulas that we know. So this is the integration by substitution technique, which I typically call simplification by substitution. All right, well, that was a lot of words for one problem. I'm going to try to talk less when doing the next problem and try to kind of show you the straightforward way of solving these. So hopefully my explanation was helpful in part A, and I'll be doing the same things with a lot less dialogue in the example in B. All right, so in B, I have this function. I don't know the antiderivative because this is not one of my known formulas. I'm going to let u equal some part that I would like to get rid of. I'm just going to get rid of the bottom part of the fraction. So I'm going to let u equal 3 minus 4x. I'm going to go ahead and calculate the derivative because I know that I need to know what dx is every time. The derivative of this thing is minus 4, which means that dx is going to be du over minus 4. So now I can transform this integral by using substitution. I have a 1 on the top. The bottom part, the 3x minus 4, well, that's what I'm representing as u. And the dx part over here, well, that's what I calculated to be du over negative 4. So it's 1 over u times du over negative 4. Once again, the constants that are being multiplied or divided don't affect antiderivatives. So we'll just write 1 over negative 4 on the outside of this integration sign, and we get 1 over u du. 1 over u du is one of our known antiderivative formulas. It's written as 1 over x dx, but the variables, as long as the variables match, the formula is correct. So 1 over x dx is equal to ln x plus c. 1 over u du is ln u plus c. All right, so my answer here, move this window out of the way, is equal to 1 over negative 4, or negative 1/4, ln of u plus c. We do have to remember the last step. The last step is you cannot leave your answer in terms of this new variable, this made-up variable. You have to return it to the original variable. Original variable was x's, and more specifically, I know that u, it was representing 3 minus 4x. So my answer is negative 1/4 ln of 3 minus 4x plus c. And that's the integration by substitution technique, streamlined a little bit. All right, hopefully you're starting to see the patterns of how this simplification technique is. And I'm going to start showing you some more complicated versions of this and some potential missteps that students make, no matter who, occasionally. I mean, even math professors will make these kinds of mistakes occasionally, just because you're doing your best, and sometimes it just doesn't work out the way you think it is, and you have to restart over. So this is one of these kind of problems where sometimes you're just going to realize, oh, that didn't quite work. Let me try it again, and using a different technique, or basically a different substitution. Okay, so here we come to example C. We have 1 over x ln x dx. And just like we did before, let's see if we can get rid of this bottom thing by making u is equal to x ln x. We know we're going to need a derivative, so I'll go ahead and define the derivative du dx. This is a product rule, so I have to differentiate the first times the second plus the derivative of the second times the first. So I get du over dx is equal to ln x plus 1. And I can just move things around and multiply by dx and divide by ln x plus 1. And so I get dx is equal to du over ln x plus 1. X plus 1. All right, so we're going to use our u to be this bottom part. And that becomes 1 over u because we chose u to be that bottom part of the fraction. And instead of dx, we have this expression right here. Du over ln x plus 1. So this doesn't quite work out as easily as the previous problems. Like before, we ended up with like a -4, some constant that we could just take out. Ln x is not a constant. It is definitely a function, right? X is a variable, right? So we have here mismatched variables. We have u's and x's, and I don't know how to simplify ln x plus 1. I guess I could try to simplify it using this expression, but I just end up with more x's and more ln's. And this is an example of when a substitution makes perfect sense, but doesn't really lead to a simplified formula that we can anti-differentiate. So we realize, oh, maybe there's another choice that I could have made for u that will make it come out sort of more simplified. And there's definitely a version or a choice in this problem where it does come out very nicely. So I set up this problem so that there would be a natural choice, which doesn't work out because, as I mentioned before, this happens to everyone, that sometimes we say, oh, that should work, and it just doesn't work. So what's the choice I'm going to choose? Well, or use. The bottom part is definitely the problem child, right? This is what makes this thing complicated. Instead of doing all of x ln x, I'm just going to do part of it. X is not very interesting to make u be x. That's just like changing the variables. I'm going to let u be this part, which is fairly complicated. So I'm going to let u equal the ln x part. And we'll see if that generates a simplified function that we can anti-differentiate. Once again, I'll calculate the derivative. Derivative ln x is 1 over x. That means du is equal to dx over x, or dx is equal to x times du. So there's my dx that I'm going to put in for here. Of course, this is my u that I'm going to put in for here, right? U is equal to ln x, right? So what do I get? I have my integral. I have 1. The x I left alone. It's the ln x part, which is now being represented by u. So xu, or x times u, if you'd like to see the timesing symbol in there. And the dx is, well, dx apparently is x times du. So this is x du. All right, so just want to make sure people see this. We took this integral. I let u be the ln x part, put that in for u. When I calculated the derivative, I got dx was x du, and so I put that part. So this is my x du, and there's my u. Now, if you look at this for a moment, you may realize, even though we have mixed match variables, we have both x's and u's, the x's divide out. You have an x on the top divided by an x on the bottom, and x divided by x is 1. And voila, this substitution did end up simplifying the integral into 1 over u du. And that is one of our known formulas. So just as an example, sometimes your first choice doesn't quite work out like we did over here. Don't give up. Try another possibility. See if a different choice of u ends up having a better simplified result. All right, so what's the antiderivative of 1 over u? It's ln of u plus some arbitrary constant. I do need the original x variable back in here. So what is u? U is ln x. So it's ln of the ln of x plus c. That is the antiderivative of our original function, 1 over x ln x dx. All right. Sometimes people consider these kind of fun, like little puzzles, like, how can I let something be u and everything kind of rinse out in a nice way, so I end up with something which is easy to anti-differentiate. You don't have to see it that way, but sometimes I see these as kind of little puzzles. All right, we'll have many more examples to do, so let's get to them. All right, I'm going to zoom in here. All right, so I have e to the 2x over 2x minus 4. Good time to pause and see if you can think of a u substitution and see if you can work out what the antiderivative is using our simplification technique by substitution. All right, well, the u substitution I'm going to be choosing is e to the 2x minus 4. Some people may just choose e to the 2x. That doesn't quite work out. Some people might choose the like e to the 2x minus 4. I guess those are only two choices I can think of. E to the 2x minus 4 actually works pretty well. Let's see what I mean by that. I'm going to take the derivative. I have to use the chain rule. I have to solve for dx. And that's the dx I'm going to substitute in for here. And the u thing I'm going to put in for here. And I end up with, what do I end up with? I end up with e to the 2x on top. On the bottom, I have, well, that's just u. And for dx, I have du over 2e to the 2x. And once again, we have a portion here in the original e to the 2x and a portion here in the substitution, which are the same and will reduce or simplify. So we have a 2. 2's are constant, or 2 is a constant being multiplied. So I'm just going to bring it outside the integral sign, so I don't have to even worry about it. I have just du on the top. I have just u on the bottom. If you'd like to write a 1 on top, just to remind you that's 1 over u. We know what the antiderivative of 1 over u is. It's the ln. I have the 1/2 times the ln of u plus c. And then I just put it back in terms of absolute values here. I put it back in terms of the original function, in terms of the original variable. U was e to the 2x minus 4. So this is like that. And then we get our plus c. Just like that. So there's another example of integration by substitution. How'd you do if you tried it? Hopefully you're pausing every now and then and trying these. That is always my suggestion. All right, we have lots of examples here. So let's do example E. Example E looks a lot like example D. It's just kind of upside down. So maybe the answer is the upside down. It's not. Okay, so we need to figure out how to do this. And maybe a u substitution would be something like e to the 2x, because that's the bottom part. And the bottom part is kind of like nice to get rid of. That does work. E to the 2x does work. It's kind of messy. I'm not going to do it because I have another reason for showing this. Some people may choose u equal e to the 2x minus 4, and that actually doesn't work. It's just too complicated to simplify things. What I want to point out here is that not every problem is going to be simplified using substitution. We're going to be simplifying all these things, but don't just have a one train mind or whatever the expression is, right? Don't get so focused on substitution that you forget about the fact that we can just use the distributive property. This is everything divided by e to the 2x, so I can write e to the 2x divided by e to the 2x minus 4 over e to the 2x. Right, that's one of our common types of simplification, is just distributing. So I can distribute these. Because there's one item on the bottom, it's easy to divide each of the things on the top. Not so easy to divide by two things on the bottom, so the top one wasn't so good to do by using the distributive property. E to the 2x over e to the 2x is 1. 4 over e to the 2x, I'm just going to write as negative exponents. This. And this is much, much easier to anti-differentiate. We can write this in two separate parts, integral of 1 minus the integral of 4e to the minus 2x. Both of these have a dx on them. You could do integrals separately because they're separated by the plus sign or a minus sign. And the integral of 1 dx, well, that's just x plus some constant. And what's the integral of this guy over here? Well, there's no formula for e to the negative 2x. There is a formula for e to the x. The antiderivative of e to the x is just e to the x. That's formula sheet 3 on the sheet I gave right here. So when we look at our problem, we say, okay, well, this is not what we want, but maybe I can simplify it to what I want. Maybe I can use a u substitution to make this thing a single variable, right? So I'm now going to choose u to be equal to negative 2x, calculate the derivative, solve for dx, and do my substitution this way. All right, so this dx thing, this is my u thing, that's going to go in here. This is my dx thing, it's going to go in here. So I have the integral of the first part is just x, and then minus, what do I have here? I have, let me take the 4 on the outside because I don't really care about constants. E to the minus 2x is going to be e to the u, because minus 2x is our u, and dx is going to be du over negative 2. All right. So what do we end up with now? We end up with x plus c was our first part, and then we have minus 4. Well, I'm going to bring out the minus 2 as well. So minus 4 over minus 2, which I guess I could write as positive 2. And then I have e to the u du. And e to the du is, that's a known formula. So that's just going to be easy to do. So I'm running out of room, so I'll go right here. This is x plus some constant. Minus 4 over minus 2 is plus 2. The antiderivative e to the u is e to the u. And then I got another constant. So this is like my C1 and C2. You don't really need lots of constants. Let's just call them one big constant, right? So if you saw my previous video, we talked about the fact that even if you break these things into separate integrals and you get separate c's, you're just going to get some big c at the end. It's just c. Big C is the sum of C1 and C2, but we don't really care how the big C is calculated. We just know that there's some constant added on. So we have x plus 2e to the u plus some constant. We know what u is. U is minus 2x. So we're going to put in that there, and we get x plus 2e to the minus 2x plus c. Sorry for the messy work here, but that is the answer. That is the antiderivative of function e to the 2x minus 4 all divided by e to the 2x dx. So the reason I wrote e, I mean, if you did this problem using u substitution, it can work if you choose u is equal to e to the 2x. It works out not too badly, but I wanted to also show you that there are many ways to simplify, and don't forget that we have all those other tools, including the distributive property, to help us transform or simplify these complicated integrals into things which are much easier to do. We basically took that integral and changed part of it into 1 and the other part of it into e to the u du. So much easier to differentiate those two parts. All right, so for letter F, another one I have here, we have some competing choices on what to choose for u. We have the x squared on the bottom. That's a good choice for u. We have a sine 1 over x. I don't like trig functions, so that's a good choice for u. We also just have the 1 over x inside as a choice for u because it's a little fraction inside. All of those seemingly are good choices. So u is equal to x squared could be a good choice. U is equal to sine 1 over x could be a good choice. And u is equal to just 1 over x could be a good choice. And at this point, if you're first learning integration by substitution or simplification by substitution, it's hard to know which one of these is the best. Do they all work? Does only some of them work? What is going on here? And one of the big things is experience. If you do a bunch of these problems, you start getting some little rules of thumb. If you think about the derivative of sine 1 over x, it's cosine of 1 over x times some other stuff. And there's no cosines in this problem. So that's not so cool. If I think of u is equal to x squared and I differentiate, I get 2x, which is promising because there's x's in there. If I differentiate 1 over x, I get 1 over x squared, and there is an x squared in this problem. So of these three, maybe the first and the last are more sort of reasonable because the middle one ends up getting a cosine when we differentiate it, and I don't see any cosines. As it turns out, this last one is the one that works out. And if you didn't realize that, if you didn't guess that it wasn't your intuition, that's okay. The idea here is we practice a few to build up your intuition, to build up your knowledge and experience, so you'll be better at estimating or guessing which is a good substitution. And if you did choose one that didn't work out, you soon figure that out and just realize that you should choose a different one. All right, so I've given you the substitution that works the best for this problem F. Please, if you are willing, pause this video and give this one a try. See if you come up with the antiderivative using this u substitution. And then in a moment, I will write out my solution. So hopefully that will be when you come back with yours to compare it to mine. All right, so hopefully welcome back. Again, we're using u is equal to 1 over x. I'm going to have to calculate for dx as well. So I just calculate my derivative. The derivative of 1 over x is minus 1 over x squared. If you don't remember that, remember 1 over x is just x to the minus 1. So its derivative is minus 1 x to the minus 2. Many students have done this enough times that they remember that 1 over x differentiates to minus 1 over x squared. If you don't, you can just redo it the negative exponent way. I'm solving for dx. That would be negative x squared du. So there's my dx. And of course, I have my u is equal to 1 over x. Okay, so let's write out this integral. So we get straight mark there. Sine 1 over x, but 1 over x is precisely what we're representing as u. So instead of 1 over x, we have u. I didn't bother substituting for x squared, so that stays there. I did give a substitution for dx. That's the one over here. That's the negative x squared du. So negative x squared du. And this is a multiplication, by the way, not a subtraction. So remember that we're timesing by dx, and now we're timesing by negative x squared du. All right, if you haven't noticed yet, the x squared being divided and the x squared being multiplied divide out to equal 1. The negative is a constant. It's a constant of negative 1, so I'll just bring it on the outside. And what's left over is sine u du. Okay, that's one of the formulas on your formula sheet, right? The antiderivative of sine is one of our formulas. You can look it up if you want. You may remember that the derivative of sine and cosine. So here's the antiderivative of sine, it's formula number 7. It's the negative cosine. Because the derivative of cosine is negative, we need an extra negative to balance out the equation. All right, so this is going to equal negative. The antiderivative of sine u is negative cosine u. And then we get some plus c. So the negative is a positive, and I'm going to resubstitute back in for what u is. U is 1 over x. So this is my answer for F. If you did it, how'd you do? Did you figure out how to get everything simplified to a point where you can anti-differentiate it? Did you get the right antiderivative? Did you remember the negatives? There's a pretty typical, not super easy, not super complicated substitution problem. All right, well, let's start getting some more complicated integration problem or substitution problems. All right. So the last couple of problems I do in this video are going to be somewhat similar to the lab this week. So if you're getting the hang of it and you wanted to skip to the end and see some of the more harder ones that are sort of related to the lab assignment, I would recommend not skipping that last bit of the video. Anyway, it's the last page. I don't know the timestamp, but the last page starts with J and K. So J and K are going to be a little more complicated. Maybe the most complicated versions of substitution simplification. All right, so I'm going to work my way up to that way. Again, you can pause these and see if things can work out for you. G is kind of maybe a little tricky one. So a good guess for a substitution might be something like u is equal to x squared minus 4x. That's the bottom part. Bottom parts are nice to get rid of because the fraction is because there's a bottom part. So if we get rid of that, it's nice. I'm going to have to calculate for dx as well. So I get dx is equal to our du divided by 2x minus 4. All right, let's put these in here. X minus 4 stays up there. X squared minus 4x was our u. And our dx was this thing right over here, du over 2x minus 4. Okay. Just trying to write this more legibly. Okay, so if you remember algebra, the minus 4s don't divide out because it's multiplication and division that will divide equal 1, not division and subtraction, right? They got to be multiplied. They can't be subtracted in order to divide out. We can try factoring. So x minus 4 on the top, u on the bottom. Factoring turns us into some more multiplication. So that's more potential, dividing or canceling. There's a 2 that's common, so 2x minus 2. And it's not working, right? I have two different variables, x's and u's. They're not canceling out or dividing out or simplifying. So I just have one variable. So at this point, this is not a working substitution. So I have to try something else, maybe a different substitution. For this particular problem, it's another example where not necessarily substitution is the best choice. You can try using a different substitution. For example, you could try just having u is equal to x squared, or maybe u is equal to the top part, or maybe u is equal just to the minus 4x. And it turns out none of them really do much at all. You still end up with mismatched variables that don't really simplify. So what is the intent for this problem? Well, I wanted to remind you about sort of not being so single-minded focused. This problem can be simplified just by using normal factoring. So I'll write the original problem over here. You may recognize the bottom has an x in common. So I can factor out the x. And if you see that, if you see the factoring, you will notice there's an x minus 4 and an x minus 4. They're being divided by each other. This is one thing being divided by the exact same thing. All right, so those things will divide out, and that gives you just 1 dx over x, and that is the ln of x. and no substitution was needed for this problem here. So just trying to circle back, try not to get so just one-sided in terms of everything is substitution. There's lots of other techniques you'll be learning in Calc 2. And in Calc 1, we have the substitution method, plus all our other algebra simplifications that we've been learning since pre-calculus and practicing. Our H is very, very similar to G. The only difference, let me zoom in a little bit, between G and H is that there's a -2 on top instead of a -4 on top, x minus 2 versus x minus 4. In this one, if I try to factor, it doesn't work because the bottom is x minus 4, and the top is x minus 2, and there's nothing on the top that simplifies or divides out with the bottom. So this case, factoring doesn't help, but lo and behold, substitution does. So here's where this x squared minus 4x works. We've already done this before, so I'll just do it quickly. Right, same thing as before. And so even though the problems look very similar, one of them substitution worked. This one substitution is going to work well, as you'll see in a moment. The other one, substitution didn't work at all. Nothing really simplified to the point where we could anti-differentiate anything. So here's my u thing. I'm going to put that in for the bottom part. Here's my dx thing. I'm going to put that in for the top part, or for the dx part. And what do I end up with? I end up with x minus 2. I didn't touch that. The bottom part, x squared minus 4x. That's my new variable u. And my dx is this formula I solved for, du over 2x minus 4. Seemingly, at first glance, not being able to simplify because the top and the bottom are different. But, of course, we do know our factoring. We can factor the bottom. There is a 2 that's common. And if I factor a 2 out of 2x minus 4, I get x minus 2. And lo and behold, I have a thing on the top. I have a thing on the bottom. They're identical. They're being divided. They equal 1. So here's where the substitution actually works out quite nicely. I have a 2 that I'll take out in the front. And I have a 1 dx over u. And we already have done this several times. The antiderivative of 1 over x, or 1 over u du. Oh, that should not be an x. I got confused. This is u du. Maybe I said u, but I wrote x. I'm not sure. All right. So if I follow my instructions here, the x minus 2's divide out. I'm left with du and u over u and over 2. So that's this critter right here. And the antiderivative of 1 over u du is ln of u plus some arbitrary constant, which I have to write back in terms of my original variable. But fortunately, I know what my original variable is. U stands for x squared minus 4x. So this is ln of x squared minus 4x plus RC. And so the reason I did those two problems side by side is just to kind of show you algebraic simplification and substitution and how one works and the other one doesn't work, etc., on problems that may look at first glance to be very, very similar. But when you start working things out, sometimes substitution works well, sometimes it doesn't. All right, so that was kind of my idea here. All right, so once again, I'll invite you to try letter I. See if you can come up with a good substitution idea. There's an e to the 3x and an e to the 2x. Those seem to be able to simplify right away. And then I have e to the x plus 1 to the 7th. Now, multiplying e to the x plus 1 7 times, I do not want to do. So even though it may not look like it's the best, the thing that's really making this complicated is this critter right here. The fact that we have e to the x plus 1 raised to the 7th instead of just something like x raised to the 7th, that makes this thing way, way more complicated. All right, that was a little hint there. Please pause this video and see if you can come up with a substitution and with an integral. I'm going to pause the video and write out my solution, and then we'll hopefully both come back and you can compare your solution to mine. All right, so hopefully you gave that a try, and I've written out my solution. So my choice for the u was e to the x plus 1, the stuff inside the parentheses. not e to the x plus 1 to the 7th. That ends up being very complicated to differentiate and to end up substituting. But just e to the x plus 1 works brilliantly. I took this and found the dx part. Dx is du over e to the x. And I put that in for dx, and I put this thing in for the u. And I get e to the 3x on the top times u to the 7th over e to the 2x on the bottom. And instead of dx, I have du over e to the x. And lo and behold, when I start doing some algebra, all the x's divide out. I have e to the 3x on the top, e to the 2x, and e to the x on the bottom, which is e to the 3x on the bottom. And they all divide equaling 1, leaving just u to the 7th du. And u to the 7th is just one of our power rule things. The antiderivative of u to the 7th, du is u to the 8th over 8 plus some constant. And putting it back in terms of our original substitution, we get e to the x plus 1 to the 8 over 8 plus c. All right, how'd you do? All right. So the last page we have here is the very complicated versions of substitution. They do get a little more complicated, but not in Calc 1. So my last page here, I have a couple of examples of how this method gets even more complicated. And then that'll be the end of the video and the end of our work here in Calc 1, culminating in this simplification technique called substitution. All right. So here's a letter J here. We have a multiplication of x to the 9th and the square root of x to the 5th plus 9 times dx. All right, I'm going to make this just a little bit bigger. Okay. So a good choice for you is something that we'd like to simplify. So this square root thing is very nasty. I don't know what the square root of x to the 5th plus 9, and if I could wish it away, I certainly would. It would make the problem much easier. Letting u be the whole square root thing, you'll learn is probably too much. It doesn't quite work out. But if I just let u be the inside part, it does work out quite nicely. So x to the 5th plus 9 is my version for u. So the inside square root part is what I'm going to be substituting for u. And let me go ahead and calculate my dx as usual. So far, it doesn't look very much different from anything we've done before. So once again, the technique is always the same. Just the algebra and things like that, the difficulty of the substitution, they get ramped up. Now here's my u, here's my dx. I'm going to throw them into my formula. So x to the 9, I did not switch, did not change. And I have a square root of, instead of x to the 5 plus 9, I'm going to write u. And instead of dx, I'm going to write du over 5x to the 4th. Okay. Well, we have two different variables, and the x's on the top and the x's on the bottom, I mean, they simplify a little bit, but they don't like divide out. They don't cancel out like we saw before. So let me show you what we can do, though. The 5 is just a constant. I'm just going to bring it on the outside. If I have an x to the 9 divided by an x to the 4, if you remember your pre-calculus simplification, that's x to the 5th. We still have our square root u and du. So if you hadn't seen these kinds of problems, you might give up at this point saying, oh, it didn't quite work. However, after seeing this technique, you will hopefully double check this each time. The thing that we're left over with, this x to the 5, right, which shouldn't be there because we can't have x's anymore in order to do our antiderivative formula, that is basically what we started with. It wasn't really x to the 5, it was x to the 5 plus 9. So we did write this substitution. This is a formula. It says whenever you have u, you get x to the 5 plus 9. That's the same thing. U is equal to x to the 5 plus 9. We can do algebra on this equation. It's an equation. I can add 7 to both sides. I can multiply both sides by 2. I'm not going to do either of those things. I am looking to see what x to the 5 is. There's my x to the 5. So I'm going to subtract 9 on both sides. If I subtract 9 on both sides, on the right-hand side, I have x to the 5. On the left-hand side, I have u minus 9. So I know what x to the 5 is in terms of u. X to the 5 is u minus 9, which makes our integral now, instead of the integral of x to the 5, I have u minus 9. I still have my square root u and du. So this sort of level of difficulty of substitution, after you do the substitution and you simplified, if you still have some things left over, make sure to double check the original substitution to see if you can solve for that thing. In this case, x to the 5 was left over, but it was actually fairly straightforward to solve for x to the 5. When I solved for x to the 5, I got u minus 9, and so I could complete the substitution of all the x's turning into u's by writing x to the 5 as u minus 9. And it turns out all we have to do is simplify this a little bit more using algebra, and we can anti-differentiate it. So here's a 1 over 5. I'll just remind folks that the square root of u, let me rewrite this. I don't know what happened. This is u minus 9. Let me remind folks that the square root of u is just u to the 1/2. And I can distribute. U times u to the 1/2, that's u to the 1 times u to the 1/2 is u to the 3/2. 9 times u to the 1/2 is 9u to the 1/2, and du. And each of these is a power rule. So I get 1/5. The antiderivative of u to the 3/2 is u to the 5/2 divided by 5/2. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. And then I get my plus c at the end. All right, so almost done. I just need to simplify this answer a little bit, combine like terms together, and then rewrite my final answer using the original variable x instead of this new variable u. All right, so I get 3/5 times 1/5, so this becomes 3/25 u to the 3 or u to the 5/2. All right, can't read my own handwriting. And then I get 2/3 times 1/5. Times 9. Okay, so this is 1/5. This is 9. That is divided by 3/2 is the same as 2/3. So if I have 1/5 times 9 times 2/3, I get an 8 on the top and I get a 15 on the bottom. Okay, that's a thirds. Jeez. Okay, 2/3. 1/5 from here, 9 from here. Divided by 3/2 is times 2/3. So I have 1 times 9 times 2 on the top, which is 18. And I have 5 times 3 on the bottom, which is 15. I guess this can simplify. I'll do that in a second. And then I have, what about u to the 3/2 plus c. All right, and then I can rewrite my, I can simplify my fraction and rewrite my answer in terms of what u is, what the original variable is. Remember that u was x to the 5 plus 9. So I'll be writing this now with x to the 5 plus 9s in place of u. So 3 over 25, u to the 5/2 becomes this x to the 5 plus 9 to the 5/2. 18 over 15, I can divide the top by my 3. So that's 6 over 5. And then u to the 3/2 will be my x to the 5 plus 9 to the 3/2, and then my lovely plus c at the end. And that is sort of a complicated version of our substitution, but also the antiderivative of the original problem. So just to kind of recap, what I did here is I did the normal substitution process. I found something complicated, let that be u. I found my dx, so I could substitute that stuff in there. I simplified, and not everything simplified the way I was hoping. There are still x's left over, but checking back to the original substitution, I actually can solve for what's left over. What was left over was x to the 5, and I can solve for x to the 5. It was just u minus 9. So I substituted in. Now I have only u's. I don't have any x's. There's no problem with mismatched variables. And now a little bit of massaging with some algebra, with some distributive property, and I can anti-differentiate this no problem. So that's the kind of level 3, I guess, difficulty of simplification by using substitution. I have one last version of this sort of, what I just call level 3. I don't know why I made up level 3. This new version, or a new complicated version of simplification by substitution. this one right here. So if you think you see the process, you can give this a try. Even if you don't think you see the process, um, give it a go, right? Just give it a try. There's nothing to lose, right? Let U be some complicated part you want to get rid of. Do your DX thing, have things cancel out. As I've mentioned, this is one of these problems where not everything simplifies. And so you can go back to your original substitution and see if you can solve for whatever's left over and get rid of that as well. And then anti-differentiate the resulting function you get. Give it a try. I'm going to pause the video and write up my answer. Hopefully, you will pause the video and write out your answer. We'll come back and you can see my steps and see if you got the answer I got or if you got stuck along the way. You can see where perhaps you can unstuck. So in the future and on Lab 10, hopefully you'll have less problems and be able to solve it no difficulty. All right, with that rambling, I'm going to pause and write out my solution. All right, so welcome back. For this problem, I used a U substitution of 1 minus x squared, that stuff inside the parentheses. I solved for my dx, and I put these into, or I substituted them. I put them into the formula. And I got this thing right here in red. The x cubed on the top and the minus 2x on the bottom is simplified a little bit. I took the minus 2 or minus 1/2 out in front, and I have an x squared and an x and a u to the fourth, right? So I have two different variables, but if you look at the x squared part, if you look at the part that wouldn't go away, that's actually pretty similar to what we started with. We started with 1 minus x squared, and that's an x squared. So that's a big tip that we can just solve for that leftover part, that x squared. So solving for that x squared, I got x squared is equal to negative u plus 1, or 1 minus u if you prefer. And I substitute that in for the x squared, getting negative u plus 1 times u to the fourth du, distributed, anti-differentiated, put it back in terms of x's, and there's my answer over here. Positive 1 over 12, 1 minus x squared to the sixth, minus 1 over 10, 1 minus x squared to the fifth, plus c. How'd you do? How far did you get? Well, you'll have some more practice on this in the lab assignment. Certainly, you can reach out to me if you have any questions or want to go over anything else. And I hope you have an enjoyable day. And hopefully, I'll talk to you soon. And good luck on the final exam.